Hello, dear listeners. I'm here to represent you my graduation project named Energy Complexity of Finite Automata as Verifiers. So, first of all, what are verifiers? Here you see a diagram of an interactive proof system consists of two parties, one verifier and one prover. As you can see, verifier has two tapes and one header for each tape to scan the symbols on these tapes. One is so-called input tape and the other one is certificate tape. Verifier, with his finite state control program, tries to verify if a string given in its input tape belongs to a specified language by checking the certificate given by the prover. So here, as you can see, there is a message exchange between two parties. So why is this message exchange is important? Because we see the prover as an omnipotent party with unlimited computational ability. Prover gives some hints, a certificate to verifier to check whether the input given is the member of that specific language. So by using this certificate, verifier with a little probability of error can verify whether the input in this tape does belong to a language. So for example, we may say that verifier is a polynomial time bounded finite state machine, but with the help of the certificate given from the prover, a verifier may give some conclusions about the membership of languages in the subset of NP languages. So main motivation for the energy complexity comes from the fact that every bit of information lost during a computation causes a dissipation of heat to the system. This fact can be applied to the case of verifiers, as you can see. Here, in the current configuration, let's say that a verifier is in state Q3 and in its input tape reads symbol sigma 3 and gamma 3 in its certificate tape. So here, looking at this configuration, if we can certainly discriminate between set of all possible predecessor configurations and say that current configuration can only be reachable from just one predecessor configuration, we definitely say that there isn't any information loss and current configuration is reached from that specific state. But if we cannot make this discrimination, we absolutely do say that a certain information is lost during this computational step. In our research, we set the criteria to spot these irreversible computations just by looking at the finite state diagram of this automata. So here you see the conditions which makes the computational step taken to bring the verifier to state Q3 irreversible. After detecting these criteria, we have examined the most known languages verifiable by a probabilistic finite state machine. So here you see one of the examples of a reversibly computed verified language. In our conclusions, we can say that the most well-known languages are reversibly verifiable, and we do leave open questions for further research. Thanks.